Lecture number 4. I'm going to give you 6 examples of volcanic landforms. And what we're going to see is not all of these landforms are volcanoes. And as a matter of fact, the first one is not a volcano. It is a landform feature called a flood basalt. And literally, it's floods of very fluid lava out of deep earth fractures. And of course, lava cools very rapidly. It's a form of extrusive igneous rock, and ultimately these floods form layer upon layer of basalt rock as these lava flows cool. Now, the way that we get very hot and fluid lava is by getting it very, very close to the Earth's surface with a geologic feature called a hot spot. Now, this is not in meteorology, it's in geology, and it's an area of upwelling of the magma of the asthenosphere. Now, remember, in the upper mantle, the asthenosphere layer containing the magma, can be found maybe at a depth of about 40 miles below the Earth's surface. But it's believed that some areas of the asthenosphere, the magma is superheated, and it can actually melt the rock of the lithosphere above it. And so you can wind up with, what they call a mantle plume, where the magma is, very, very close to the Earth's crust. Right? It can even melt into the Earth's crust. So you can actually have magma, maybe within a mile or less of the Earth's surface. And so all you need is, fissures and fractures, over an area. It can be a vast area, like in Washington State here, and you can have flood after flood of lava. And so I'm going to give you an example for each of these 6 features. The best example in the United States. And for this example of flood basalts is the Columbia Plateau, mainly of Washington State. Here it is here in Washington State, basically eastern Washington State, just to the east of the Cascades. Now, it does extend into Oregon and a little bit into Idaho. And what a plateau is simply an upland surface. In this case, through lava flow after lava flow, we have built up a plateau 10,000 feet high. Now, it took a long time to do that. It took about 10 to 15 million years for this lava flow after lava flow to build up, a 2-mile high plateau. And here's a little picture of a section of the Columbia Plateau where the Columbia River has cut through. And you can actually see some of the basalt rock. Remember, it's kind of dark in color. And here's a lava flow here, and here's one here, and another one here, another one here, another one here. And here's just another picture of a section of the Columbia Plateau where we've got some erosion that exposes some of the lava flows. Here's a nice example of one lava flow, and here's another one here. Now, I'm still talking about flood basalts. There is a very characteristic feature, right? And it's called columnar jointing. And what they are contraction cracks. They're vertical joint spaces in flood basalts. And sometimes the vertical joint spaces, the forming columns, can be perfect. So perfect that they almost look man-made. And really what they are contraction cracks, kind of similar to mud cracks. If you think about, you've got a mud puddle, and the mud dries up and contracts and forms these cracks. And just kind of imagine the same thing with lava cooling and contracting and forming, these kind of cracks. And so you wind up with, if you imagine now from the surface, tens of feet down, you wind up creating a column, in the shape of the mud cracks. And here's kind of an image of that. Here's a flood basalt. Actually, this is in Northern Ireland. And there was a flood of basalt that went into the ocean. And so the ocean waves and the tides, have eroded the flood basalt. And so here we can actually see the surface. And literally, this is the columnar jointing. And it literally looks like mud cracks. And that's my son when he was little, when we went to Northern Ireland. But anyways, here you can actually see, some of the columns here, where we've got some waves eroding. Oh, it's fun. You just kind of jump all around on all the columnar jointing. All right. Now, the second volcanic landform is a volcano. is a volcano. It's called a shield volcano. And now we're finally going to get to the Hawaiian Islands. Now, definitely, right, the Hawaiian Islands are shield volcanoes. That's our big example. And this is when you've got lava flows, flowing out of a seafloor hotspot that builds up, right, after, flood of lava after lava, basalt on the seafloor, and building up until the lava layers actually make it above sea level and continue to build and build and build a volcano above sea level. Right. Basically, this is the same thing as a flood basalt. You've got a mantle plume where you've got a hot spot very close to the Earth's surface, and you wind up with very hot fluid lava spreading out over vast distances. But in this case, instead of doing it on the land, it's doing it on the seafloor. All right, so this type of volcano is called a shield volcano because, once the lava flows, make its way and build up a volcano above sea level, it takes kind of a low domal shape, right? And kind of in the shape of a warrior shield. And here's the shape of, of the big island of Hawaii. And it's just a low domal shape. Let's talk about the formation of the Hawaiian Islands. Now remember, the Hawaiian Islands, did not form at a plate boundary. It's not at all associated with subduction. The Hawaiian Islands are found right in the middle of the giant Pacific plate in the Pacific Ocean. And there's been a persistent hotspot, and it's actually called the Hawaiian hotspot. And there are about 40 or 50 hotspots that exist on Earth today. This is just one of them, and it's named the Hawaiian hotspot. And it's persisted here for millions of years, something like 5 or 6 million years. And so we've got this stationary hotspot, but what is not stationary is the plates. And so the giant Pacific plate has been slowly moving over this hotspot, and what it winds up doing is creates, a volcano, right? It builds up from the seafloor and then eventually above sea level to make a volcanic island. Then the plate moves and you wind up, right, with that volcano becoming extinct, and then it starts to build another volcano. So it's kind of like a conveyor belt, as this is describing. And so so this would be the island of Hawaii today, and then the next island kind of to the north is Maui, and there's more islands above sea level, right, in the Hawaiian island chain. But it is kind of amazing that the island of Hawaii, built up 20,000 feet from the seafloor to sea level. 20,000 feet. I mean, that's 4 miles of floods of lava, right? Flood basalts, literally. And then, once it made it to sea level, it has built up an additional 14,000 feet. And so the big island of Hawaii, I mean, its maximum elevation is 14,000 feet above sea level. So that is just a massive, massively tall, volcanic mountain. I mean, it's basically 34,000 miles high from the seafloor to the summit. Yeah, and so here's just the Hawaiian island chain. And so Hawaii, right here, the big island, it's right over the Hawaiian hotspot, so it's active. But then all of these other volcanoes are now inactive as they've already moved to northwesterly away from the hotspot. And so these are the more familiar, the main Hawaiian islands, Hawaii to Kauai. But in actuality, the Hawaiian island chain extends, greatly to the north west, all the way to about Midway Atoll, Midway Island here. And here's just another example of the Hawaiian hotspot where the island of Hawaii is quite active. And then the ages, and some of the oldest ones are, over, this is 5.6 million years old. And so it's been existing. This hotspot has been persistent for many millions of years. And this is just an example of showing how Hawaii is, the youngest and the active volcano. And then as you, move farther away from the Hawaiian hotspot, the islands get progressively older and older. And I just kind of want to make a point here about relief. If you remember when we were doing plate tectonics and talking about creating relief on the Earth's surface, as it turns out, relief in the oceans is much greater than relief on the continents. If you think about it, from sea level on the continents, the highest point in the Himalaya Mountains, Mount Everest, is just over 29,000 feet. And so that's our maximum relief on the continents, 0 sea level to 29,000 feet. But in the oceans, if you remember, so here's sea level, our deepest ocean trench is the Mariana Trench that goes down 35,000 feet. And then you've got volcanic islands like Hawaii, right, that is built up above sea level, in this case, 14,000 feet. So you've got relief in the oceans, well over 35,000 feet when you consider the elevation, of the volcanic islands in, say, the Pacific Ocean. All right, let's move on to the landform number 3, and this is another volcano. And as a matter of fact, of these 6 volcanic landforms, there really are only 2 true volcanoes. And so the shield volcano of Hawaii and this type. All right, so this next landform is a stratovolcano. Now the shape of this has the classic cone shape that you imagine a volcano to have. Now the other thing about stratovolcanoes that you absolutely need to know is these are subduction zone volcanoes. So I've already shown you pictures of stratovolcanoes in regards to subduction zone volcanoes when I was illustrating the Cascade Mountain volcanoes and the Andes Mountains. And I had actually shown you some pictures. Remember Mount Rainier and a volcano in Ecuador. And here's another one. Right, and so they're subduction zone volcanoes. Now the reason why they're cone shaped, it's because that they're layered, and actually they're stratified. They're layered with layers of ash, volcanic ash, and layers of lava, and so they're stratified or layered. That's why they're called stratovolcanoes. And so sometimes these volcanoes will explode, crushed up rock, right? It's crushed up into dust and will, extrude, tons and tons of ash, and you start to build a cone. And then other times, it'll have a massive lava pluming up from the asthenosphere, and you'll have a lava flow. And other times, it'll explode out and crush up the rock and explode it out as ash or dust. And so you'll have different layers upon layers of ash and lava. And it's believed that these interlayering creates strength, so you can build a tall classic cone. And here's the crater, right? And what a crater is just a central depression of the main vent of the main vent. And so of course when it's not filled with lava or ash, it's open, and so it'll form a depression, a central depression. I just want to give you a couple more examples. I mean, there are literally thousands, of stratovolcanoes on the Earth's surface. But here's a famous one, Mount Fuji, and it's snow-capped in wintertime. And you can actually see it from downtown Tokyo in Japan. And of course, the islands of Japan are an island arc, and a beautiful example of stratovolcanoes. And people love to hike it. It's a very, it's a very touristy thing to do. If you ever go to Japan and Tokyo, you'll definitely take a trip to Mount Fuji. Here's another stratovolcano in Costa Rica. It's called Arenal volcano, and it's active, right? And it's been flowing lava for decades now. I mean, I stayed there. I mean, it's amazing. There are resorts and hotels in the tropical forest with hot springs, and it's really, a beautiful place to go. I mean, a lot of people like to go to Costa Rica now, and it's just amazing that it's a big resort town, and they allow you, to actually see an active volcano. So apparently the geologists know that, this is not a violent, the chemistry of the lava is not going to be form a violent eruption, apparently. Okay, landform number 4. It's called a caldera. And this is a huge central depression after a violent eruption of a stratovolcano. Right? So it's much larger than, the original crater. Right? That little central depression at the top. Stratovolcanoes are known to have violent eruptions, and it's based on the chemistry of the lava. And sometimes you can, have violent eruptions where it's going to, crush up the rock, and you'll have, spewing out tons and tons of ash. But in some cases, the magma chemistry is such that you wind up with almost like an atomic explosion that after, it has built itself up, a big, tall volcanic cone over millions of years, literally, right, the volcano blows itself up. It blows itself up. The magma chamber, the upwelling of the asthenosphere, becomes totally evacuated. Right? All the magma is gone, and everything just kind of collapses back on down and around. And I've kind of added to this diagram. I kind of drew in the caldera. This is all that's left. The only thing that you'll have left is maybe the rimming base of what was once the former stratovolcano. And you wind up with a huge central depression called a caldera. The best example in the United States is a national park. It's called Crater Lake National Park in Oregon. Now it's in southern Oregon in the Cascades, and this is a national park. It really has the wrong name. I mean, it should be called Caldera Lake National Park, not Crater Lake. But anyways, it does have the wrong name. But what you can see is kind of the base of the former volcano. Now, this volcano was named Mount Mazama, and it erupted about 8,000 years ago, and it blew itself up. It was, about a 12,000-foot volcano, and all you have is the base. And now you wind up with a giant caldera that's 6 miles by 5 miles. And it's very, very deep, right? It's actually the deepest lake in the United States. At its maximum depth, it's 2,000 feet deep. And, the depth of this lake, gives it, crystal blue waters. And that's what makes it really quite famous. Well, anyways, so this caldera, this very, very deep, a feature, in a wet area, you've got orographic precip, fills in with water. So you don't necessarily have to have a caldera filled with water, but in this case, in a well-watered area, you wind up with a lake. And so this is, and I'm gonna, there's a little island, and that'll be our final landform. Landform number 5 is a volcanic neck. And it's an erosional remnant of an extinct volcano. And so only the only thing that's left is the main lava chamber or lava vent. All right, lava, here's some lava vents, going to the main lava vent. And the best example, is a volcanic neck near the Four Corners area in the United States in New Mexico, and it's called Shiprock. All right, and it's amazing that there was once a giant stratovolcano here, a giant one, and the hot spot died off. It dissipated, all right, cooled, or moved on, and so the volcano goes extinct. And then erosional forces over millions of years take over. And today, what we have in the United States are many fine examples of volcanic necks. I mean, the western United States was very, volcanically active during the time of the dinosaurs, during the Jurassic period. And the hot spots have dissipated, and you wind up with many, many fine examples of volcanic necks. Now, this one is enormous. I mean, this is an aerial view. In Shiprock, New Mexico, I mean, the summit is 7,000 feet. So this is an enormous feature. And it's called Shiprock because it is so big. I mean, you could be, I don't know, miles and miles away on an interstate, and you can actually see Shiprock from a great distance. And from a distance, it almost looks like the sails on a ship, sailing it in the desert. And there's another example in the western United States in Wyoming. It's called Devil's Tower. And this one is not as tall as Shiprock. It's about 1,000 feet tall, and it's an erosional remnant. The only thing that we have left now from erosion is the main lava vent. And here you've got beautiful examples of columnar jointing. All right, and here it is. Here's the columnar jointing up close, just to kind of give you the scale. And so the columns in this case are enormous. And here's some rock, this is what people love to do, are rock climbers, climb up and maneuver somehow, in between the columns and make it all the way to the summit. So that's kind of a neat thing. All right, the sixth and final landform is a cinder cone, and it's a hill of ash. And it says they're made entirely of ash. They're not going to attain the great heights, of volcanoes that are, 10 or 12 or 17,000 feet high. They're only a couple hundred feet high normally. And so what winds up happening is you need a volcano in the area. And what you wind up is with radiating vents that can extend, maybe 50 miles or more away from the main volcanic vent. And sometimes these vents make its way to the Earth's surface and spew out ash. And it's basically raining of ash, all right, from a vent that's going to build up an ash cone, of cinders. That's why it's called a cinder cone. And this one is in the United States. This is in northern Arizona, and it is a national park. It's called Sunset Crater National Park, in Flagstaff, Arizona. And Flagstaff, Arizona is kind of the gateway to the South Rim of the Grand Canyon. So if you ever go to the South Rim, you'll go through Flagstaff, and there's a couple of national parks there. But it's called Sunset Crater because this one cone, you can't really see the crater from this angle, but here's an aerial view. It's called Sunset Crater. This is the same one, and it has sulfur at the top near the crater. And the sulfur, makes it, an orange color, and it looks like the sun is setting on it. But in the distance, there are literally hundreds or even thousands of cinder cones. So if you ever drive from Flagstaff to the South Rim, just kind of take note. You'll see, hundreds of these cinder cones. Yeah. And then I just want to kind of go back to Crater Lake National Park in Oregon, Mount Mazama. After Mount Mazama, erupted and exploded, eventually a fissure opened up and spewed out ash. And ash built on up, creating a little island in the lake, in the Crater Lake, or in the caldera actually, and it's called Wizard Island. And so that's kind of the, I don't know, the famous feature. Another famous feature of this caldera is this little cinder cone in the middle of the lake. End lecture.